Hi guys, welcome back to Data Every Day. Today we're looking at a data set of loans. I don't think we can see the preview right now. I'll try refreshing. But if not, we'll just get right into the notebook. Basically, it's a data set about people who have loans, and we're going to try to predict whether or not the customer has paid off their loans or not. So let's hop into the notebook. We're going to use 6 different models to make our predictions, namely these ones: logistic regression, support vector classifier, decision tree classifier, multi-layer perceptron classifier, or also neural network, random forest classifier, and an XGBoost classifier as well. So I'm using NumPy and Pandas just to work with the data, and then I'm importing the standard scalar and train test split function from sklearn for pre-processing. So let's go ahead and import those, and I'm going to load in the data using pandas.readcsv. And we can get the CSV file path right here. I'm going to copy it and paste it in, and take a look. Alright, so we have 11 columns. You can see we have at least one unnecessary column. This isn't going to give us any useful information, it's just an ID number. So we're going to want to drop that. Additionally, we have 1, 2, 3 categorical columns, and we also have 3 date columns. So we're going to do some amount of encoding and feature generation from the date columns, and we also have some missing values that we can see. So let's get a little info on the dataset. Looks like not too many missing values. It is important to note that we only have 500 entries in this data, so we're not working with too big of a set, but it's still enough to train models on. So 400 and 200 here. So it looks like there's 100 missing values in paid off time, which is the date column, and 300 missing values in past due days, which is a numerical column. So for this one, we're just going to fill with the mean. Alright, let's start pre-processing. So lately I've been making this pre-process inputs function, which we're just going to put all of our pre-processing in there, pass in the data frame, and have it return an x and y, where y is what we're trying to predict, and x is what we're going to use to predict it. So we'll start by creating a copy of our data frame, and then I'm going to split the y off from the data frame. So y is loan status. This is what we're trying to predict, right? We want to predict if they've paid off the loan or not. We can actually take a look at all of the different values in loan status by doing loan status.unique. And you can see there are 3 unique values: paid off, collection, and collection paid off. So essentially, if you take a look at some of the information here, collection is they're still trying to collect the loan and the customer has not paid it off. This is they have paid it off without being put into collection. And this one is they paid it off but after collection efforts were made. So we're going to try to predict one of 3 labels. And a good thing to do first let's just get the isNA. So isNA on its own will just show us the same data frame, but a true or false value if there's a missing value in a given location. So we have a true here because there's an NaN there. If we sum across the rows, it's the same as summing up all the trues in each in each column. So we get the number of missing values in each column. And we can see we have 100 in paid off time and 300 in past due days, as we saw above. Last thing I'd like to do to just gather a little information before we dive into the pre-processing is I want to get a dictionary that maps a column name to the length of the unique values in that column. That way we know how many unique values we're dealing with in each column, and we can investigate further after that. So that's for every column in data.columns. Here we go. You can see so there's 500 uniques in here, so this provides no useful information since it is categorical and everyone has its own value. There's no similarity between data points that's captured by this column, so we can drop it. Additionally, you can see, I believe this is a numerical column, so we don't have to worry about that number. But everything else seems reasonably small. These 3 actually are date time columns. Okay, So I guess let's start by dropping that loan ID column. So to do that, we just do df equals df.drop loan ID, and we're dropping from axis 1, that's the column axis. And I want to return x and y, so why don't I just create those now. Y is going to be the loan status column, right, this one. What we're trying to predict is these three values. So I'm going to make y be df sub loan status, and I'm going to make a copy of it and store it in y. Then x is just going to be everything except loan status, so I'm going to drop it from axis 1 and create a copy and store that in x. Now we'll return x and y from this function, and if we now create an x and y using the function, pre-process inputs, passing in data, we can take, oh, loan ID not found in axis. So maybe oh yeah, there's an underscore there, so I just got to put that in. Note that if we don't use this line, then we still have the loan ID, but now if we drop it, we see it's gone. So now we're making progress and checking the results by running our data through this function we're creating. Alright, so I guess let's next do the date and time columns. So these two columns do not have a time value, and this one does. So what I'm going to do is generate some new features from the existing date time features. So why don't I just comment this, drop loan ID column, and then over here split df into x and y. And now we're going to create date/time columns. So first thing to do, for column in, I'm going to get all the date columns: effective date, due date, and paid off time. df subcolumn equals df subcolumn, equals pd dot to date time df subcolumn. So to datetime will convert this string into a datetime object, which will allow us to reference the year, month, and day directly just by typing, referencing them as attributes, so .year, and so on. So once they are turned into datetime columns, all we have to do to create these new features is df sub, how about we do this? We'll call it effective, and we'll just copy this 3 times, make one of them year, make one of them month, and make one of them day. So we're creating 3 new columns here, and each one is going to be some sort of transformation of the original column. So equals df sub effective date dot apply, and we're applying a lambda function element-wise to each value in the effective date column. So x represents a specific value, and because we transform them into datetime objects, we can just say x.year, and that will automatically give us the 2016 value. Then we'll just copy that over for each one, except this will be x.month, and this will be x.day. So if we run this and take a look, you can see we now have the year, month, and day columns that we generated from here, and you can see the values match up. Okay, so let's do the same thing for the other two. So I'm going to grab this and do this and this. So let's call these ones due year, due month, due date, due day. So I'm going to copy that, and we'll just do like this, paste, and these ones are all referencing due date. So paste that in like that, and that should accomplish the exact same thing. We're making 3 new columns taken from the due date column, where each one is year, month, or day respectively. So let's just take a look at that before we move on. And you can see we now have these 3 as well, taken from this column here, 2016, 10, 7, 2016, 10, 7. So now we know it's working. Let's do the last one. This is paid off time, so I'm going to call it we'll call it paid off year, paid off month, paid off day, like that. And then I'm just going to paste this in for these ones. That should do the same thing. However, I want to make one more. Because this has time data as well, we also have hour, minute, second information. Now, I don't think minute and second is very useful, but the hour may tell us something. For example, some people may be more likely to pay off their loans in the middle of the night, as opposed to others who are paying it off during the day. I'm not entirely sure, but it might be useful to have. So we're going to create this one that's paid off hour. And we just here type x.hour. And there we go. So let's run that. Okay, we have these year, month, day, year, month, day, year, month, day, hour. And you'll notice that these are actually floats, whereas before we had ints. And usually if you see that, if something gets converted to a float like that, it's usually indicative of missing values somewhere in the data set. And we actually know that there were missing values in this column. Paid off time had 100 missing values. So luckily, datetime still allows for missing values, but everything has been encoded as floats, and that's simply because numpy.nan, I believe it's considered a float. Yeah, it is. So that's why we have these as floats, but we should now work on filling the missing values. Before I do that though, I just want to drop the original date columns, which we now no longer need since we have encoded them as their own individual columns. So I'm going to say for column, I'll just grab this again. For each of these columns, actually no, I'll just grab this and say df equals df.drop, paste in the list, and then drop that from axis 1. Now you can see we don't have the original date columns, but we have all this information added on the end. Alright, so let's deal with the missing values now. If we take a look at this, so I want to check the sum, but afterwards, after the processing is done, so I'll change data to x, and you can see now we have 4 columns with 100 missing values. Those are the 4 that we generated from the original column that had 100 missing values. So now, because they're in numerical form, we can actually fill them with the means of each column. So this as well, because this is numerical, we'll just fill the missing values with the mean of the column, the mean based on all the other values. Now I know this is a very high percentage of missing values, but I feel that because we have such a limited set of features and not too much data, it would be too wouldn't be good to drop the column. So why don't we keep the column on and just fill the missing values. So over here, we'll fill missing values with column means. Okay, so for column in, and now I want to target all of the columns of missing values. So we have past due days here. We have, and then we have all of the paid off columns. So paid off year, paid off month, and paid off day, and paid off hour. Now for each one, we're going to say df subcolumn equals df subcolumn dot fill na. So this function will fill all the missing values in the column with a given value, and the value we're going to give it is the mean of the column. So now we run this and we check the missing values. We have no more missing values. So we're good to go. Right, next, I believe we are ready to encode the categorical features. So there are actually only 2, right? Let's take a look. I want to get, so up here we have the number of unique values in each column. So I'm going to modify this a little. Down here on the process data, instead of data, I'm now looking at x, and instead of getting a length, I want to get a list. So I want to see the actual unique values in each of the categorical columns. And note I said categorical columns, so we're not just going to get it from x.columns, but x.select dtypes object.columns. So this is going to get only the columns where the data type is an object, or in other words, a string. So it will only target these 2 columns, and for each one, we'll get the column name matched with a list of the unique values in the column. So we can see what kind of values are in each of the categorical columns. So it looks like this is obviously a binary column, so we can binary encode this, which just means we'll set one of the values to 1 and the other to 0, and that's all the column will become. With education, this looks like an ordinal feature to me, because there's an order between the values and there's more than 2. So we can rank this high school or below, then college, then bachelor, then master or above. It has like a progression. So we need 2 encoding schemes, binary encoding and ordinal encoding. So up here above my preprocess inputs function, I'm going to create these 2 encoding functions. First, a binary encode function, and we'll also do a ordinal encode function. So each one works a little differently. They're both going to take in a data frame, and the binary encode function is also going to take a positive value. And the positive value is just going to be whichever value we want to assign to 1. So like I said, one of the values will be 1, the other will be 0, and we're going to specify which one we want as 1. So to do this is very simple. First, I just want to make a copy of the data frame so that we're not modifying in place. And then I'm going to take, we actually have to pass in a column as well, a column that we'd like to encode, and then the positive value associated with the values in that column. So df subcolumn is the column we want to work on, and I'm going to apply a lambda function to the column where x represents a given value in the column, and we're going to change x to 1 if x is the positive value, and otherwise we'll set it to 0. So this is the encoding right here. It's either 1 or 0 depending on if x is the positive value. And then we can just return the data frame after that. That's all it is. Now for the ordinal encoding, we also want to specify a column, but then we also need to specify an ordering. And the ordering is basically just going to be a list of the of all the unique values in the column, but in the order that we want to encode. So in this case, we would order these values here in the order of progression, and then we'll pass that in. So now I'm going to make a copy again, and then we're just going to take this essentially. This is also just one line, but we're not going to apply this lambda function. Instead, we're going to apply a lambda function that takes the ordering and then plugs in our x, which is a given value in the column, to the index. So we're indexing x in the ordering to get the integer associated with the order. So if we have, let's say we have some list 1, 2, 3. No, that's no good. How about we have a list 9, 9, 9, 9, 8, 8, and we index at 9. It returns 0. Oh, let's make this 7. If we index at 8, we get 1, and if we index at 7, we get 2. So over here, we're just taking in a given x, indexing it in the ordering, and getting back an integer that represents where in the order it is. And then we'll return the data frame, and that will be it. So these are our 2 functions that we're going to use, and now we'll encode binary column. Well, actually, let's say binary encode the gender column. And then all we have to do is say df equals binary encode, that's the function we just wrote, passing in the data frame, gender as the column, and then the positive value we're going to give is going to be, well, we can look down here, male or female. Male is the convention for positive for the 1, so we'll set the positive value to male, and then we will we don't have to binary encode any other columns, but we're now going to ordinal encode the education column. Right, that's this one here. So I'm going to take the values here, and I'm going to create an ordering, education ordering. And let's just format this a little. Okay, I'm going to sort them now into the order, and they're almost there. I think college just has to come before bachelor, like that. So it goes high school, college, bachelor, master, in that order, and then we're going to say df equals ordinal encode df education, that's the name of the column, and the ordering is going to be the education ordering. Alright, so let's see. Okay, it did not work. Why? Gonna check up here, make sure everything's good. df equals. You can see it did not encode. So I'm actually a bit confused. We ran this, right? Alright, give me 1 second, I'll figure it out. Yes, I found the problem. It was a very stupid problem. When I tried to apply the function to the column, I did not actually set it to be the new column. So the same thing for both of them. Just have to make sure we say df subcolumn equals the transformation. Okay, so now we can see gender has been encoded as 1s and 0s, whereas before it was male and female. And the education, which used to look like this, now looks like a series of numbers. I believe it should be 0 through 3, because there were 4 total values. So now you can see there are no more object columns. And the last thing to do in terms of encoding is encode the labels, which this is our y, this is what we're trying to predict, and it's going to take off one of these 3 values, paid off, collection, or collection paid off. So for this, I'm not going to use ordinal encoding, although I could. I just want to do something more simple and easy to understand. So we'll say encode the label. Where is it? Loan status is the name of the label, right? Yeah, loan status. Column. So for this, I'm just going to create a label mapping, which will be a dictionary that maps each of the values to a integer. So it's the same as the ordinal encoding, except I just want to explicitly define which value is mapped to what, just so that we can see it. So I'm going to have collection as the 0 value, because that essentially means nothing was paid off. So we're going to map that to 0. Paid off, they did do it, we'll map to 1. And then collection paid off means they paid it off, but only after collection efforts were made, so I'll make that 2. And so this is our mapping, and all we have to do is say df equals df.replace. No. Just doing this on the loan status column. Df sub loan status equals df sub loan status dot replace, and all we have to do is pass in the dictionary into the replace function. Label mapping, and it will automatically apply the mapping to every value in loan status. Alright, so let's run this, and run this, and you can see our y is now encoded as 0s, 1s, and 2s. If we check the unique values, we can see that for sure. And last thing to do is to scale our x. So I'm going to do that after we split. I'm going to scale x with a standard scalar. So the standard scalar, this is the one I imported earlier. This is going to give each column in x a mean of 0 and a variance of 1, which will allow each column to take on a very similar range of values, which we can do like this. So scalar equals standard scalar, create a new object, and then x equals scalar dot fit transform x. So this will fit the scalar to x, and then it will transform x accordingly so that each column has a mean of 0 and a univariance. And then I'm going to turn it back into a data frame, because this actually returns a NumPy array. So I'm going to turn it back into a data frame and keep the columns as they were. Alright, and then I think we're done. Let's take a look. Alright, it's fully scaled. There is something I notice here. If you ever scale the data and you see that there's all zeros in the column, that's a very good indication that the column only had one value. Because if there's no variance, if everything is on one value, then that just gets shifted to 0, and then all the values take on 0. So I want to do a little more of an investigation here. I'm going to get, like I did earlier with this thing, let's get the length of unique values except in X. So this now tells us in this process version how many unique values there are in each column, and as we can see, in all the 0 columns we have only one value. So a column with one value is not of any use to us. So we're going to drop those columns. Effective year, effective month, paid off year, and due year. Right. So let's go up here, and all we have to do is just not use these. So for effective, it was year and month, so we're going to drop year and month. Just don't generate those. Then due year is one as well. Getting rid of that. Then paid off year is the last one. Getting rid of that. Alright, now I'm running this one more time. Oh, what happened? Oh, okay, because I tried to reference it down here. So we just have to make sure we take that out of there. Okay. Alright, now we have removed those columns. We no longer have zeros in any of the columns. And if we look at the length of values in each one, we no longer have columns with only one value. Alright, so everything is ready to feed into the model. We have a scaled, clean dataset with all the features we can use, and our labels, which are encoded as 0, 1, and 2. So let us begin training. Alright, so I'm going to first, I guess one last pre-processing step that I'll include in training is to split this set into train and test sets. So for this, I'll use the train test split function from sklearn. We're going to generate 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And that's train test split of x and y. We'll specify a train size of 70%. So 70% of the data is going to go into the xtrain and ytrain, and the other 30% is going to go into xtest and ytest. Additionally, this function also shuffles the data, so we don't have to do that ourselves. And we can include a random state here to ensure the shuffle and the split is always done in the same way. So 1, 2, 3, it can be any number, just so that we can reproduce it. So I'll run that. We now have these 4 new sets of data. Let us create our models and fit them. So I'm going to use 6 different models, these ones here. So I'll just copy and paste from my other notebook all the models we'll use. These I imported at the top. I just have them in a list here called models, and each one is a new instance of the classifier. So there's 6 different classifiers: logistic regression, support vector machine, decision tree, neural network, random forest classifier, and an XGBoost classifier, extreme gradient boosting. So what we're going to do is iterate through and fit each one. So for model in models, model.fit, and we're fitting it on the train set, so xtrain, ytrain. So that should fit all 6. It's done. There's very little data, so it took a very short time. And now what I'll do is I'm going to get the names of the models and store that in another list. I already have it, just the names of each one. And then I'm going to print out the results like this. For model, name, in zip of models and model names. So this zip thing, if we look at that, let's run this, and then let's take a look at just the zip. Oh wait, hold on. Let me copy it down here and turn it into a list so you can see what it looks like. Okay, yeah. So it basically links up the 2 lists. Here's one list, right? Here's another list. It links them, it pairs them up element-wise so that we have tuples consisting of each pair of values. So down here, logistic regression, the model has been linked to the logistic regression, the name, and then the model to the name, and so on. So we now can iterate through 2 at a time like this to get the model and name at the same time. So with that, we're going to print out the name followed by a colon, a space, and then a formatted number here. We'll show it to 4 decimal places and put a % sign after. This is going to be the accuracy value. And .format, we're plugging in the accuracy value, which is given by model.score. This will be for a given model and for a given name. And we're scoring it on the test set, so X test, Y test. Alright, let's see what we get. And here are our results. Oh dear, this is not percentages. I have to multiply it by 100 first. Now we can see. Alright, and it looks like 4 of our classifiers maintained 100% accuracy, and 2 of them are closely behind with a 98.67% accuracy. Looks like decision tree neural network worked well as the 2 ensemble methods we used, and the logistic regression and support vector machine did not work as well. That will sum up today's video, though. I hope you enjoyed it. Thank you so much for watching. If you did enjoy the video, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.